All right, so this is part 2, where I'm actually going to do some of the problems in section 7.1. And for each problem, I'm going to make a table that has 5 values in it. After I make the table, I'm going to sketch a graph. And at some point, I'm going to say what the domain and the range of the graph is. And I should know everything right now except the y part of my table and what the points on the graph are. So because the exponent is just an x, the x column of my table is going to have -2 to 2. So to get started on problem 2, my x's are going to be -1, -2, -1, 0, 1, and 2. The y's I need to get using either by hand or using some sort of technology. All exponential functions have domains of negative to positive infinity. So the domain of this is going to be negative to positive infinity. And because there isn't a number written after the exponent, the range is going to be 0 to infinity. So now I'm going to get the y's for my table. And I'm going to do this one completely by hand. I kind of wouldn't suggest doing that, but just to show you that you can. So this second column here, I could either put a y up top, or I could write g of x. It doesn't matter. And for the first value of -2, if I wanted to find the y, I'd go g of -2 equals 2 to the -2 power. If I wasn't using technology, I'd say 2 to the -2 power is 1 over 2 squared. And 1 over 2 squared is 1/4. I could leave that as a fraction. I can make that as a decimal. That's 0.25 as a decimal. The instructions say round to 1 decimal. I'm just going to leave this at 1/4. And I'd probably just leave it there. For the next one, g of -1 is 2 to the -1 power, which is 1 over 2 to the first power, which is just 1/2, and as a decimal that's 0.5. Then a g of 0 is 2 to the 0 power, and any number to the 0 power is 1. And then g of 1 is going to be 2 to the first power. Anything to the first power is itself. And then g of 2 is 2 to the second power, and 2 to the second power is 4. So I can see that when I go to make my y column, if I look at my y's, there aren't any negative y's, and my biggest y is 4. So for my y's, I'm just going to march them up to 4. If my table had more values in the x's, then I might have to plot y's that are bigger than 4. Like if I put a 3 under here, I'd get 2 cubed, and the next y would be 2 to the third power, which is 8. But that's not going to be the case. If I put a -3 in, I'd get 2 to the -3 power, which was 1 over 2 cubed, which is 1/8. The y's going in this direction would be like 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. The y's going in this direction would be 2, 4, 8, 16, 32, 64 for what that's worth. Let me just plot these points the best I can. The first point is x equal to -2, y equal to 1/4. So x equal to -2, y equal to 1/4. I'm just guesstimating that. I'm not going to write any of the points down here because it just gets so ugly. And then the second point I'm plotting is x equal to -1, y equal to 1/2. So there's -1 and about 1/2. And then x equals 0, y equal to 1. X equal to 1, y equal to 2. and x equal to 2, y equal to 4. All exponential functions kind of have a similar vibe in that they get real high on one side and they flatten out on the other side. Usually on the side that they flatten out, that side gives me the bottom of the range, and this left-hand side is flattening out. So if I write my axes in here, this is the x-axis, this is the y or g of x axis, and this graph, the next point would be negative 3 1/8, negative 4 1/16. Each of the y's are going to be microscopically above the x-axis. Each of the y's is going to be positive. No y is ever actually going to be 0. When I go to graph these exponential functions, I don't know how well this is going to work. I'm trying to pull out a new marker here. The bottom of the graph I usually designate with a dashed line. And the bottom of this graph is going to be the x-axis, because each of these values right here are going to be really, really small fractions that are progressively getting closer to 0. So on the left-hand side of this graph, it's going to get super, super close to the x-axis, but because the y's are always positive, they're always bigger than 0, the graph will never actually touch the x-axis. So the left-hand side flattens out and gets microscopically close to the x-axis, and the right-hand side shoots up really fast. The next point, if I was to plot it, would be 3 and 8, and maybe that would be up here somewheres. So this would be a reasonable graph. I put little arrows at the edges, meaning the graph keeps going in the direction. The right side goes up really, really steeply, really high very quickly. The left-hand side never actually gets a y that's negative, so the graph never goes beneath the x-axis, and actually never gets a y that's 0, so it never actually touches the x-axis, because points on the x-axis have y's equal to 0. The graph will stay microscopically above the x-axis, and the y coordinate of any point on the x-axis is 0. And so when I go to write the range, the bottom of the graph is the y coordinate of the x-axis. It gets a round bracket at that because the graph never actually gets, there's no point on the graph that has a y of 0. There's just points that their y's get super close to 0. And the top of the graph goes to the top of the y-axis, which has a y of infinity. That's a bit of overkill. When you do your problem 1, you could do something similarly. You can get all the y's by hand, or you can start using your calculator to get some of the y's. The next graph I'm going to do is problem 4, and I'm going to have you do number 5, so let's maybe bust those out a little bit. So immediately, when I look at the graph for number 4, or the function for number 4, the exponent has a minus 2. I'm going to put positive 2 in the middle of my x column, then go smaller and bigger. The domain for all exponential functions are negative to positive infinity. The range, if there isn't a number after the exponent, is going to start at 0 and go to infinity. So for problem 6 that I'm about to do, I'm going to start off doing a table. And in problem 6, that minus 2 in my table, I'm going to change its sign, so the function, just in case it's not showing up so well, is 4 to the x minus 2 power. I'm going to change the sign of the exponent and put a positive 2 in the middle of my x column. Go smaller and then bigger. I'm going to get lazier in terms of finding my y's, and maybe I'll start throwing some decimals in here. I'm going to write my domain and my range down before I actually do the graph. Every function that we're going to do, the domain is negative to positive infinity. And if there isn't a number written after the exponent, the range is 0 to infinity, which means the bottom of the graph is going to be the y-axis. The graph will get microscopically close to the y-axis, but it will never actually touch the y-axis. So I'm going to maybe color this differently. So when I go to do this graph for problem 6, on my x-axis I need the numbers 0, 1, 2, 3, and 4. And I'm going to show the bottom of this graph with a dashed line that goes through 0 on the y-axis, and 0 on the y-axis is actually what the x-axis is. This is going to be the bottom of my graph. The graph is going to get super close on the left-hand side to this dashed line. It will never touch the line. It will always stay microscopically above it on to the left of the y-axis. And the right-hand side is going to get real high. So for each of the values now in my x column, I'm going to get a y. And I'm not going to do them as by hand as I did last time. So for my first x, I need to plug in 0. And I'm going to get 4 exponent 0 minus 2 power. And my y is either going to be 1/16, or if I hit the SD button, 0.06. It says round to 1 decimal. So let me just try to round that to 1 decimal. I'm going to say or 0.1. This 6 is going to round the 0 up to a 1. Next thing I'll do is f of 1, which is 4 to the 1 minus 2 power. And that gives me 1/4. It says to round it to 1 decimal. That frustrates me, that instruction. If I'm gonna do this as a decimal, I'd probably leave the 2 decimals, even though it says to do 1 decimal. That would technically round to 0.3, but I can graph a quarter pretty accurately. So this would be one option for finding y's, is just one line at a time. Plug the number in and get its y. I'm just doing these kind of silently now. So here are the y values next to my x values. So the points that I'm supposed to plot are the point 0 and 1/16, the point 1 and a quarter, the point 2 and 1, the point 3 and 4, and the point 4 and 16. I don't feel like plotting the point 4 and 16 because I don't want to make 16 marks on my y-axis, so I'm just going to kind of wave at that and maybe not plot it perfectly. And I'll plot the other points decently well. So the first point is 0 on the x-axis, up 1/16, and 1/16 is just a hair above the origin. I'm starting at 0 for x and going up. If I made 16 marks between 0 and 1, just one of those marks. And then 1 comma a quarter, that's a half. Half of a half is a quarter, so that's about 1 comma a quarter. And then 2 comma 1, 3 comma 4, and then 4 comma 16 I'm not going to plot. And here, the next point, if I was going up, would be -1 comma 1 over, I think, 64. The point is, going up or going this way, the y's will never be negative. The y's will always be 1 over something, 1 over 64, 1 over 256. The y's will always be positive, so the graph will never touch the x-axis. The x-axis has a y equal to 0, and the bottom of the graph will be the x-axis. And so as I go to try to graph this, I'm going to try to make my graph as close as I can on the left-hand side to the x-axis, but I'm going to try to stay microscopically above the x-axis. And then on the right-hand side, I'm going to just sweep it and make it really high. The point 0.34 I have on here, not done so well. And then 4/16 would be way up here somewheres. So this would be not the greatest graph ever. It shouldn't have these little wiggles in it. It should be more like that, but it is what it is. It doesn't have those little wiggles. It's smoother. So that's a reasonable graph. I I think you can do problem 11 without me doing 10 or 12, and so I want to do the backward graphs next, which are the graph. So I'm going to skip, I'm not actually going to graph number 10. I'm going to come down and do 22, but you should do number 11 just for practice. And the table that you would do for number 11, you'd change the sign of that plus 3. You'd have -3 in the middle of your x column, then -2 and -1, -4 and -5. The domain for all exponential functions that we're going to graph is negative to positive infinity. And because there isn't a number written after the exponent, the range is going to be 0 to infinity. The x-axis is going to be the bottom of the graph. What's more interesting is graphing these fractions, like in problem 17 and problem 18. Maybe I'll just do 17. Well, yeah, I'll do 17 with you. As opposed to doing, oh, that's not problem 22. Well, maybe it is. Yeah, it is problem 22. Let me do 17 with you. So in 17, if I was going to graph it, I know because the exponent doesn't have a plus or a minus, that the table that I'd get would have a -2 in the middle, would have a 0 in the middle of the x column, and I'd get smaller and bigger. So on this sheet that I put on the first part of the video, if the exponent is just x, like in problem 28 and in problem 20, you use the -2 to 2 table. And that's the case here. In this problem, the exponent is just x. For all the graphs that we're going to do today, the domain is going to be double round bracket, -infinity, comma, positive infinity. And for most of the graphs that we're going to do today, the range is going to be 0 to infinity. If there isn't a number written after the exponent, the range starts at 0. If there's a number written after the exponent, the range starts at that number. When the base is a fraction, the graph goes backwards, meaning it gets high on the left side, low on the right side. So let me fill out my, well, let me get my table graph started here, and then I'll start my table. So on my x-axis, I need 0, -1, -2, +1, and +2. The bottom of this graph is going to be the y-axis, so I'm going to make a dashed horizontal line on the y-axis, and that just signifies that the graph is going to get real close to this, but it's not actually going to touch it. Now for each x, I'm going to get a y. So for my first one, I'm going to do g of -2, which is 1/3 to the -2 power. If you didn't have a calculator, you could say this is 3 over 1 squared, which is 3 squared, which is 9. So my first y, if I did parentheses, fraction 1 over 3, parentheses, exponent -2, I'd get 9. My second y, I do g of -1, which is 1/3 to the -1 power. And 1/3 to the -1 power is 3. My third y would be 1/3 to the 0 power, and anything to the 0 power is 1. Idiot. So I get the point 0, 1. And then my fourth y is going to be 1/3 to the 1 power, or first power, and anything to the first power is itself, so I'm going to get 1/3. Or you can make that into a decimal like 0.3, and then I'll plug 2 in and get 1/3 squared, which is 1/9. If I hit the SD, I could write 0.1 as a decimal. Kind of like the fractions if I can get them. If I'm using the table feature on my calculator, I'm going to get decimals. I'm okay with plotting decimals. Let me plot these real quickly. I'm only going to plot these points because I don't want to get up to 9. I need to get my y-axis up to 3 to do the points that I'm going to graph. The first point is -1 comma 3. This point here that I'm not plotting, -2, 9 would be up there for what it's worth. And then 0, 1, 1 comma 1/3, 2 comma 1/9. When we have fractions as my bases, the graph goes backwards. It gets high on the left side and gets low on the right side. Still, the y's will always be positive. As I went down this list, it'd be 1/27 for a y, 1/81 for a y. If there isn't a number written after the exponent part, the x-axis is the bottom of the graph. So that's everything for 17. I'm going to pause and do a part 3 to this.